Hi again, everybody, and welcome to our first session of the 2024 Robotics Application Conference presented by Corber. Thank you for joining us for our keynote presentation, and now we're going to make our way into our machine vision and object detection track. My name is Tim Culverhouse, and I'm the editorial director of Robotics 24/7, and I'll serve as the moderator of this session and all other sessions of RAC 2024. Now, today's session is titled Mastering Parcel Variability, Leveraging Human-AI Symbiosis for Optimized Logistics. Now, before we begin this track, I'd like to thank our sponsor for it, and that's Plus One Robotics. Also, before we begin today's presentation and discussion, let's go over some of our housekeeping. First, if the slides accompanying today's discussion aren't advancing, please hit the F5 key to refresh your browser window. Viewers who'd like to download a PDF of today's slides and other supporting documents from our sponsor, Plus One Robotics, can do so by clicking on the blue paperclip resources box at the bottom of your browser. You can also access these resources on the Machine Vision and Object Detection session page. Now, if you're still experiencing other technical difficulties with today's program, please click the orange question mark box at the bottom of your console for further help and instructions. Now, the e-commerce industry is booming, and logistics providers are struggling to keep up with increasingly diverse and unpredictable streams of parcels. Now, this presentation will explore a synergistic human-AI vision system that can effectively mitigate the complexities of parcel variability. Now, to speak about these issues and highlight the value of humans and AI vision systems with robotic systems, I'd like to introduce our guest for today's program. And our guest is Dr. Dan Grollman, Principal Software Developer at Plus One Robotics. Dan, thank you so much for joining us as part of Robotics Application Conference 2024. And over to you.
Thanks for having me, Tim. So just a first little background on myself and the company. So I've been working in the robotics space for quite some time now, particularly in how humans and robots can work together to sort of get better outcomes for all. It's one of the exciting things about here at Plus One Robotics, where we say robots work, people rule. So a little bit about us. We've been around for a while. I've been here at the company about 5.5 years now. We work in the warehouse logistics space. So how do we get robots to move things around warehouses in a way that makes them cheaper, faster, better, more efficient? We combine computer vision, artificial intelligence, and supervised autonomy, what we call human in the loop. We've done this quite a lot. We've got over 1.3 billion picks worldwide so far, and we've been doing this since 2016.
So Dan, I know part of today's presentation is really going to focus on the logistics side of things. And can you elaborate a little bit more on what robotics applications Plus One offers that support logistics?
Sure. We do two main things. The first one is induction. So here's some pictures to sort of carry that around. We take goods coming in on a conveyor belt, like you might see here on the bottom, and we have robotic arms pick them up and put them one at a time down on an outbound conveyor. And this is to make downstream processing easier. You want to handle the packages one at a time as they come through. You can see here we use cameras and vision to find the objects. You can see the blue, green, and red and yellow boxes there that we've discovered with our vision system, and then we tell the arm where to pick it up and where to put it down. The other application we do is depalletization, which is very similar, except now we're working off of a pallet of goods. So these tend to be heavier, bulkier. These could be boxes filled with anything you might find in bulk, toilet paper, seeds, peanut butter, things like that. Dog food is a popular one. And again, we use computer vision to find the objects, tell the arm where to pick it up and where to put it down. The idea being to turn a pallet of goods into single items for future handling. Now these tasks seem fairly straightforward, but it's also important to note that during the process of an object or a parcel getting from when it is made to whoever the final consumer is, these things happen a lot. So here's some pictures to illustrate how many times a single parcel could be touched. It comes in off of a boat, off a shipping container, it is unloaded, it is put away, it is then taken off the shelf, put into a box, sent to a distributor, where it is then unloaded and put away, and then can be taken off the shelf again. This can repeat on and on for about an average of 20 touches per object, per parcel that is shipped. So these problems of induction and depalletization happen continually and repeatedly throughout the entire logistics lifestyle.
So we've got a lot of visuals associated with this slide, and you just referenced how many different people, specifically humans, are touching this box stand. And from the robotic side of things, what are some of the common challenges that you would experience when you're using robotics for these sorts of applications and movements that are all associated with taking a box, a parcel, and moving it further down the logistics time?
Yeah. So the first thing is these tasks, this depalletization induction tasks, these are the traditional 3Ds of robotics. It is dirty, it is dangerous, and it is dull. And so it is ripe for automation. I've got a little video here that's been circling around on social media just to show you like what it's like when people have to do this. So I'm gonna just play this for you. I can see us holding hands, walking on the beach, our toes insane. I can see us on the countryside, sitting on the grassland side by side. You can be my baby, and you can be my baby. Yeah, you can hate me, ain't gotta do nothing crazy. So that made the rounds on TikTok, and that is people doing this job of taking parcels from a pile and putting them into singles. And you can see how that is, it's dull, right? You're just doing the same thing over and over again. It's dangerous also because we all know repetitive motions can cause serious problems for your health and your body. And it's dirty because you're in a warehouse just handling things, you're getting sweaty, there's dust in the air. It's just not good to have people do this. So we're really thinking automation can help out here. And there's two main problems, two main challenges that automation needs to address. So the first one that you see here is throughput, is how many of these things can you handle in a given amount of time? People are ordering more and more things online. People are shipping more and more things across the world. The global economy is getting faster and faster. So we need to move these things through the logistics network as fast as possible, right? And so the other one is entitlement. And this refers to how many different sorts of things can you handle. So we're seeing a increase in the variety of stuff that has to be handled via logistics. So here are some pictures. These are actual pictures from our systems. We see that it's no longer just brown boxes. We have bright orange boxes. We have teal boxes. We have all sorts of colors. And it's not just boxes. We have cardboard boxes. We have polybags. We have paper mailers. We have a whole variety of shape and size and color and material, all of which needs to be handled. And so entitlement is how much of this stuff can your system manage? And so we want to increase throughput. We want to go fast enough to keep up. We also want to increase entitlement. We want to be able to handle more and more things. And these things are usually in odds. So you can get high throughput if you're always handling the same thing. It's very easy to automate just handling the same object again and again and again. And you can use robotics and automation and computer vision and machine learning to get high entitlement, where you can handle a lot of things. But all those technologies take processing time and take power and decrease your throughput. And of course, the most obvious way is humans. Humans can handle all sorts of things. We've got these wonderful grippers that we call our hands. We get great entitlement, but we're limited in our speed because we're only human.
So I know one thing that we've talked about offline and with roboticists in general, how humans are going to be involved in some way, shape, or form with parcels and logistics and materials handling. But you spoke about the variability of the parcels and where we are with robotics and automation right now. Is that something with that variability automation can do by itself, or are we still going to need that human interaction involved somewhere?
Yeah, so we can do some of it ourselves. So computer vision has actually been a wonderful field when applied to logistics. It's been seeing such growth over the last decade, at least, and even beyond that. And so we use a lot of it, and a lot of companies use computer vision to deal with this variability, right? So computer vision is basically the process of taking this image, and here's an image of just some identical brown boxes, and figuring out where is each of the things that I care about. So we've gone ahead here and we've just colored each pixel according to which box it belongs to. And once we can do this, we can tell an arm or some sort of automation, here's the thing you care about, how to handle it. And now that gets us a lot of variability. That gets us variability in terms of location. So objects can shift around and we can still do it. It gets us some variability in terms of visual appearance. So, boxes can be darker or lighter. They can be square or rectangular. We can handle a lot of variability just by using the technology that we have.
So another part of this variability conversation, unknown variability. When you're having all of these boxes coming down the line, where can we dive in further about unknown variability in its relation to the problems that it causes both humans and automation in the logistics space?
Great question. So, right, what I'm showing here is how we can deal with sort of variability in visual appearance. Variability that we might be able to predict in advance. Like I can tell you, oh, maybe the box will be here, maybe the box will be there. It might be shaped differently. But we're doing such wonderful things that there's a whole bunch of variables that I can't predict. So one of the things is we keep changing our packaging, right? So it used to be everything came in brown cardboard boxes, but now all sorts of new things happen. Part of this is driven by environmental concerns. We want to ship lighter materials. So we use less fuel. We want to ship more recyclable materials. And so we're always experimenting. We, people, are always experimenting with different sorts of packaging technologies. So over here on the left, you see I get these bags all the time with a notification that it's lighter than our smallest box. That's a push to ship less mass, so we get fuel savings. We also do them more recyclable. So I get more cardboard and more paper mailers because I can now recycle those in my curbside recycling. There's also a big push towards what's been called SIOC, or ship in its own container, which is instead of taking the parcel and then putting it in another box to ship that, so the box is the same and so the box is sort of anticipated. It's a cardboard box. We now ship them just as they are. And that leads us to those brightly colored packages. That leads us to brightly patterned packages. It leads us to packages of different sizes and shapes. And we're still coming up with new things. I know there's always been some researchers looking into how do we make more biodegradable packaging? How do we make packaging that is more easily reused for something else? So I can't tell you what we're going to see in the future. I can't tell you what packaging is going to look like 5 years from now. And so the systems have to be able to adapt to them.
And now on that front, Dan, you're talking about getting into advanced technologies, your artificial intelligence, your machine learning sort of thing, while also the variability of the packaging materials that, as you just said, we can't predict that. How is Plus One utilizing AI, machine learning to ramp up its objectives with object detection and make this a little bit easier than what we're doing right now?
Yeah. So one of the things we do is we actually involve humans in the solution to these challenges, right? Humans are sort of the source of some of these challenges because we're always innovating. So we use humans to resolve the challenges as well. And this is the system that we call Yonder. It's a Human-AI Symbiosis system that lets humans intervene in real time to correct for exceptions in autonomous handling. So over here on the left, you see sort of expected behavior. Heaps of things come in. We've got an arm, we've got cameras. They find the object, they handle it. The symbols come out, either on a conveyor belt or on a mobile platform or something like that. And that can happen very quickly. And that's how we get high throughput, right? We have the automation do the basic thing again and again and again, very quickly, very repeatably. But when something new happens, when a new package is encountered or a new scenario is encountered, the system calls for help. The system just calls out to a human. This human is remote, they're someplace else in the world, and they can resolve the problem. They can perform that same visual task of finding the object. And they can do it in the human way, which is they can do it very flexibly. They can deal with all sorts of new packages and then new visual appearances. And they provide that back to the arm, and then the arm continues. And that's how we get our entitlement. So this is how we increase throughput and entitlement at the same time. We let the autonomy, the robot, and the human both do the parts they're really good at, symbiotically, and then we get a system that can outperform either one individually. Now, behind all of this is, of course, like you said, machine learning. right? So machine learning, and I'm talking specifically here about computer vision with a deep neural network. There's a lot of different types of machine learning. This is the specific use case we're doing here. And it's all about finding patterns in data. And the traditional way to do machine learning is you collect a lot of data. You annotate that data with the information you care about. So here we found some pictures of animals, and we've drawn some boxes around the cow and the tree, right? So these are objects. This is an object detection task. We then do a lot of math. We turn the crank, we do a training system, we get a model out, and we deploy that in the field. And if it all worked well, the autonomy, the robot, the arms, can now see the objects that we annotated and handle them appropriately. And if you need to do this again, you can do this again. You collect data, you annotate the data, you train the model. You can do this repeatedly. And this takes weeks or months to turn this system around. And it's tough, it's a lot of math, but really, this is a graph from The Economist a couple of years ago. The bulk of this time is spent in just the data management part. This part here on the left, getting the data and annotating the data. About 80% of your time is spent dealing with your data, while 20% is actual training the model. Now, why is that so much time? It's because there's humans behind it. The way to get this annotation is very often to pay humans to sit at a desk, looking at a computer, drawing these boxes around objects. Or what we actually do is individually label pixels in an image with which object it belongs to. This is dull work. What we've done is we've taken the dullness of working in the warehouse and moving packages around, and we moved it to the dullness of labeling images. It's a more comfortable dullness for sure, right? You get to sit in an air-conditioned office on a comfortable chair. In many ways, it is better than moving packages around in a warehouse, but it's still dullness. And it's sort of not really nice that we've just traded one sort of dull work for another. So why is this so difficult? Well, the annotation, getting experts to do this is so hard and time consuming. Here's an example. So this is an image from our data set. This is a pile of polybags. There are, I don't even know how many polybags in this, but if we ask a human to individually label each polybag with a boundary, this takes a long time. This takes minutes. And if we have a data set of millions of these, and we do over 1 million picks a day, that takes a long time to label. So we don't. So we've developed this system we call the single annotation paradigm. So we see here on the top right, you see that fully labeled image where someone has gone through and spent several minutes annotating each individual object. But it's much easier to ask, just annotate one. First of all, it's less annotation. I have fewer things to do, so I can get it done faster. Second of all, I can choose the easiest one to annotate. I'm not going to choose something really difficult and bunched up and maybe hidden something else. I'm going to find the object that is the easiest thing to annotate that and get it done. And so we've changed sort of the request we have from the human. Rather than asking for the best possible answer, we're just asking for what's an adequate answer. Just give me enough to go on. And don't give me the complete answer. Just give me the quickest thing you can give me that lets me keep doing my work. And this way humans, can do less, the job becomes easier. And conveniently for us, this is exactly what we get during operation with our Yonder system, where when the autonomy runs into trouble, it asks the human, and the human provides a single response that is just enough to get the system back on track. We do this, we actually have to do one more step to be able to use it. So when we take single annotation images, if you tried to learn on that, if you did traditional machine learning on that data, you don't get good results. So over here on the right, you can see that if you do traditional learning on a data set like ours, you can get an average precision of about 92%. Now, average precision here is just a metric of how well has the model learned your data. Higher is better. If you take the single annotation and you try to do traditional learning on it, you get 0. That's really bad, right? The system doesn't learn anything at all. What we can do is we can take this single annotation that we get from our crew chiefs. We can combine it with data that we already know, in this case, a blank background, and we can create a new data set that is fully annotated by applying various transformations to the images to make packages look like they're different places. And if we train on that data, we recover 75% average precision. That's not as good as 92%, that's for sure. But since there's no additional annotation, we can deploy much, much quicker. And that's the thing that people often forget is the amount of time it takes you to actually get the model that you need. So here's our appropriately titled fancy graph of entitlement versus throughput. I told you those are the two metrics we care about. We also care about cost a bit. Humans are up here, top left. Great entitlement. Humans can handle anything we throw at them. Humans really are wondrous things. But they're slow because they're limited by muscle speed. All the way here on the other axis, on the lower right, we have a robotic arm handling identical packages. Blazingly fast. We can get such high throughput, but we're limited by what we can handle. Now, if you follow the traditional approach to automating this with machine learning, you're going to take 3 weeks to collect your data, annotate it, train it, and that's this gray line. And for those 3 weeks, if you were in operation, you'd need to be paying humans to do your task. The humans would be there, they'd be doing it while you were working behind the scenes to get your model going. And then 3 weeks from now, you put your model into production, you'd get your 92%. Great. Humans would still have to handle that last 8% probably. But what we offer with our approach is we can get you 75% on day one. And then the next day we can improve on that. And the next day we improve on that. And we just keep getting better and better and better. So we might approach that 92% in 3 weeks. But also while we're doing that, we've taken over so much of your handling. Humans only have to handle 25% on day one, and then maybe only 20% on day two, etc. And so if you're looking at the area under this curve in terms of savings, we've saved you everything under the curve by having a system that doesn't perform as well as it possibly could, but performs quickly and then keeps getting better. So what we call this system, we put it all together, this is adaptive symbiosis. So it's a human and an autonomy system working together to adapt as things change. We start with a model. Generic model doesn't have to be able to handle everything. We get this exception data from the system when it calls for help. We don't have to do any additional annotation, so we can very quickly turn around a new model and put that into production. And so we just keep getting better and better and better. This is fully automated, hands-off adaptation of the system.
So excuse my entitlement. I am making a pun of the graph from the last slide, but you're describing this model here in front of us. And simple question, but if you're implementing this, how do you know that the model is done? Like, at what point do you know that your model is set and ready to go and deploy and you can tinker after it, but you're not in that preview mode beforehand?
Yeah, so the short answer is you're never really done, right? We expect things to always be changing. And that comes from sort of two different sources of variability. We talked about people making changes to how we do packages. You can see this up here on the right. This is what we call distributional shift or distributional drift, where the things you need to handle are changing over time, right? Maybe today you're handling small cardboard boxes and those lighter than smallest package bags. But then Black Friday happens and everyone's shipping large televisions because they went on deals or they're buying appliances. So the distribution of things you handle has changed. Suddenly you've got these larger packages. Or maybe people have developed a new sort of packaging, or there's some new advertising push and the colors of all your packages have changed. And so your whole distribution has shifted. And that might be temporary, right? That might come back. So you've got this distributional shift where you're always sort of trying to guess what's the next thing that I'm going to see. We also have what we call long tails, right? Even if you weren't changing anything, there's things that are just so rare that you hardly ever see them. Most of our packages are brown boxes or envelopes or bags. Occasionally we see something that's six-sided. Occasionally we see something that's brightly colored. Even occasionally we see something that's got pictures of a dog, or maybe someone has shipped an actual potato through the mail. Right? These are very rare cases that if you try to get enough data to train up ahead of time, you've got to go collect a lot of data to get that. But if you can handle it in an adaptive fashion, you just deal with it as it shows up. If it never shows up, you never have to handle it. So here's some examples of things we've actually seen in our production systems that we now need to handle. So you can see we've got broken pallets, right? So pallets break and they just keep using them. Boxes open up. So here, the lower left, the tops of these boxes have been sheared off. So now you see what's inside. There are spills. Over here on the left, those are some sneakers on an induction belt. Why there are sneakers on an induction belt, I do not know. They fall out of a package. Did someone try to ship sneakers? We have to deal with that. And I've got some data to sort of back up this claim. So these are, what you see here is a bunch of different models on the left. And across the top is time. Those are dates. And we see that over time, any fixed model degrades in performance. So if we start at 4.1 and we're doing pretty good at 97%, by late June, we've fallen to 91%. And this is true for all the models. They all degrade over time. And that's proof that the things we're handling no longer conform to the data that this model was trained on. It's drifted. And so we have to keep retraining models just to maintain performance. And that's what we've done here. So each of these models going down has been trained on additional data. And you can see our very first model, even back in April, was only at 69%. We train a later model, we jump up to 97%. So we keep having to bring in this new data. We have to keep adapting to the shifts in our distribution.
This is giving me flashbacks.
Yeah.
I was just going to say, this is giving me flashbacks to algebra class and why I decided to go into writing as compared to math with this. But
fair enough. I see this table, I get very happy, but it's not for everybody.
The PhD and the roboticist and the editor. This is a very, very different description of data and the day-to-day operations. You've done a lot
That's when I've got the fancy graph for you.
You've done a lot of looking back and talking about the training of the models and the technology that's out there now and what Plus One is doing with Yonder and everything else. As you look forward now, are there things on the horizon that excite you for object detection that we aren't able to handle at this moment in 2024 and moving forward here?
Yeah, there's all sorts of exciting work going on. I still go to academic conferences. I read a whole bunch of papers. There's a lot of exciting things. This is a wonderful time to be in this field. But there's two things I'm very excited about. So one is self-training, right? I mentioned we still have these humans, these crew chiefs, providing sort of, this is the thing you should be doing. And that's what our systems learn from. It would be great if we didn't have to do that. It would be great if we could sort of move humans even further up to decision-making and less of that low-level processing. And there's some work that looks at this. Reinforcement learning is a great field. Self-training in general of having the system try new things and learn from its own mistakes is just a great way to learn to deal with things. Unfortunately, we have some issues when it comes to making mistakes in production, right? So over here on the left, you can see this is from Everyday Robotics. They had to get a whole fleet of robots to just try all the different things, right? Because the robot needs to try things before it can learn from them. And even when trying, you sometimes fail. Over here on the right, you can see the Atlas robot falling on its head, right? And where we are in production in warehouses, failure is not really a viable option, right? If you have to mess up several times before you can solve the problem, that impacts your throughput. That's money. That's not something we want. So I'm excited for this. I think there's great ways to have the system learn from itself, but it's just not quite ready for production yet. The other one that's been getting a lot of news is robotics foundation models. Right? These are super exciting. These are huge models trained off massive amounts of data that generalize well across many different regimes and could perhaps, handle even more of this input stream, so we have, less for humans to do. Problem with RFMs right now is if you look at big ones, popular ones like ChatGPT, it's trained on about 10 trillion tokens, so 10 trillion words, right? And if we think of our systems, and if we're doing a pick a second, which is incredibly fast, now to get that amount of data, 10 trillion picks, 10 trillion seconds, that's 317,000 years worth of data of picks. I don't have that data. Even if I had, 317,000 systems in production, it would take me a year to get that data. I don't have that number of systems in production. No one does. So the question of how do we get the data is a problem. And I don't know if there's a good solution for that just yet. The other thing, robotics foundation models, sort of because we have that much data, we can't have humans annotating. We can't have humans in the loop to make that data usable at all, because there's just too much. And so you sort of need that first part of self-training. You need the system to be able to learn from its own data without human involvement at all in order to really be able to leverage this technology. There are great minds out there working on these problems. I'm confident we will see solutions within a couple of years, but right now we're looking at what can we put in the warehouse today, and adaptable symbiosis is, I think, the answer for today. As you can tell, we've done actually 1.3 billion picks with this system in production. This is, not quite the 10 trillion we need yet, but we're getting there.
Oh, well, thank you so much for laying out everything with machine vision and learning and object detection and AI. And one thing you mentioned again, the human element of all of this and what's going on there now. It's really interesting to see that dynamic and the relationship still continuing to grow, even as automation takes further steps down the line too, Dan.
Yeah. Well, thanks for having me, Tim.
I've got a couple questions for you, if you don't mind.
Absolutely. Yeah.
So the first one, one of the things that came up in your conversation is metrics. And I know we went through a lot of data. Again, the editor and writer here was terrified by the amount of numbers. But when organizations are looking for machine vision and object detection solutions, they outline some of the metrics that they want to have. And a lot of customers want to think about throughput, but not the time to deployment. So I'm just curious if you can elaborate on that and what that sort of thinking can affect in terms of the return on an investment and the overall success of these systems.
Yeah, it's somewhat related to the 80-20 rule, right? So the last 20% takes 80% of the effort. If you want to get full automation and full entitlement and high throughput, you can get that first 80% relatively quickly, but the last 20% takes a lot of work. And I think a lot of companies don't realize that they do a great proof of concept on that first bit, and it's quick and it's fast to get out and it works great, but to get it all the way there takes a lot of time. So that time to full deployment is, I think, often overlooked. And so one of the reasons we offer Yonder and we offer this adaptive symbiosis system is that we recognize that there's always going to be some more you could do. But if you wait until the system is perfect, or even near perfect, it's going to block you from deploying for a long time. So if you want to deploy quickly and handle most of your stuff, something like this is the way to go.
And the other question that I had for you, and this is going back to kind of the early portion of your presentation where you hit on variability of parcels that are coming down the line, and specifically the difference between anticipated and unanticipated change. Could you elaborate a little bit more in terms of the variability of parcels that are moving down the line and what robotic and automation systems need to have in place to adapt to those changes, both predictable, but then the unpredictable, like a shoe coming down the line, as you showed before?
Yeah. So we really do think you need humans in there, because humans are the ones driving all of these changes, right? Humans are the ones asking for more sustainable packaging, lighter packaging, more environmentally friendly, et cetera. And so since humans are the ones driving that process, they're also the ones sort of best situated to help us automate it and resolve it. And if you know what's coming down, if you know, hey, people are looking at changing things like this, they can then come in on the other side and say, how can we adapt to this? How can we get our systems to work? But unless we reach the state where there's just no adaptation at all, where there's no innovation at all, then I think you're always going to need some sort of adaptation. And since humans are the innovators, I really think humans should be the adapters as well. There is this view that, again, maybe with a robotics foundation model, maybe with some sort of universal model, it's certainly seen enough stuff that it can handle any future adaptation because those adaptations are minor compared to the breadth of data it's seen. I think that'd be wonderful. But like I said, we're nowhere near the 10 trillion data point mark. So I don't know when that's going to happen.
Maybe we can revisit it in RAC25 and see if we're close to the 10 trillion mark. We'll go from there.
RAC25, RAC35, sure, that feels about right.
By the time my kids are involved in robotics, then we can really get involved with it. But I'm going to wrap things up here with us, Dan, and I just want to say again, thank you so much for joining us as part of RAC24 this year in the session. It was really great. I, again, really appreciate what you and Plus One have done with this session and the conference, and I look forward to talking to you again soon. And yeah, thank you so much.
Great. Anyone in the audience has further questions, feel free to get in touch. There's my contact info right there, or you can reach out to the company directly.
And as a reminder, again, for our audience, a PDF copy of today's session, along with other related content from Dan and Plus One Robotics, can be found in the resources box on your console, along with other information about the other sessions going on as part of RAC 2024 today. Before you leave, if you don't mind, please fill out the feedback survey that's open on your console. Thank you in advance for doing that. It helps us improve upon our future events such as RAC and our webinars moving forward. And thank you again for attending this session for RAC 2024 on machine vision and object detection, titled Mastering Parcel Variability, Leveraging Human-AI Symbiosis for Optimized Logistics, brought to you by Plus One Robotics and the presiding sponsor of RAC 2024, Corber. Our other sessions will be released throughout the day. We have our mobile robot track up next, and you can follow along with everything in on-demand viewing from today and other events with RAC 2024. You'll receive some information via email at the end of all of our presentations. So on behalf of our guest, Dr. Dan Grollman from Plus One Robotics, I'm Tim Culverhouse, Editorial Director of Robotics 24/7. Thank you so much for joining us for this session in RAC 2024 presented by Corber. Enjoy the rest of the day. Can't wait to see you on our next track. Thanks, everybody. Bye-bye.